Now that we've talked about the terrestrial planets, on to the Jovian planets. So the Jovian planets are the big ones in our solar system. They're both big by radius as well as by mass. So here we see the masses of the Jovian planets. So Jupiter has a mass around 318 times the mass of the Earth. So it would take 318 Earths to get to the same mass as Jupiter. Saturn is at 95 times, Uranus is at 14, and Neptune is at 17 times the mass of the Earth. So Jupiter is by far the largest, but they're all really massive. Alright, here's our first question. The Jovian planets are superior to Earth. When is the best time to view them? A. At conjunction, B. At greatest elongation, or C. At opposition. Go ahead and think about it, and we'll discuss it in just a bit. Alright, do you remember this one? We kind of talked about it last time when talking about Mars and Venus. So the correct answer is C, at opposition. Opposition is where it's going to appear opposite the sun in our sky. So it's going to be easy to view at night when the sun's not up, but also during opposition it's going to be at its closest to the Earth. So it's also going to be at its brightest. Jupiter and Saturn are easily seen with the naked eye. There's no problem at all. And, again, because they're superior, they're going to be best viewed during opposition. Jupiter is actually very bright during opposition. It is actually only outshined by Venus. So as far as the bright things in the sky, number one is the sun, then the moon, then Venus, and then Jupiter at opposition. So it is very bright. Saturn is brighter than all stars except two. So it goes sun, moon, Jupiter, Venus, Sirius. If you remember Sirius, this is the brightest star in the night sky. Another star called Canopus, which is only viewable in the southern hemisphere, and then Saturn at opposition. So it is also very bright. Now, during opposition, Jupiter takes up almost 50 arc seconds in the sky. Now, if you remember arc second, there are 60 arc minutes in a degree, and then 60 arc seconds in an arc minute. This means that Jupiter almost takes up a full arc minute around opposition. Now, the limit of human resolution, how clear our eyes see, is about 1 arc minute. What this means is if Jupiter was bigger or closer, we could actually see that it was round with our eyes in the sky, which would be amazing. Now, because of its distance from the Sun, it takes about 12 years for Jupiter to orbit once around the Sun. What this means from our perspective is that it drifts from one constellation to another along the zodiac. It takes about 1 month or one constellation every year. So from one opposition to the next is 13 months, 1 year and 1 month. Saturn at opposition takes up about 20 arc seconds, which is about half an arc minute. So no, we would not be able to see it nice and round in the sky with our eyes, but that is big enough that it's going to be very, very bright. Because of the distance to Saturn, it has an even longer orbital period at 29 years. Okay, so what this means is that Saturn actually changes position very slowly. It takes about 2 years, a little over 2 years, for it to drift from one constellation to another. So, from our point of view, oppositions occur every 12 months and 2 weeks. Now, it is technically possible to see Uranus with your eye during opposition, and only during opposition. It barely reaches that sixth apparent magnitude limit that we need for seeing. But even then, you're not actually going to notice it. And if it's not at opposition, there's no chance of you noticing it. In fact, Uranus wasn't actually known anciently. It's a somewhat modern discovery. Neptune is so far away that it is never actually visible to the unaided eye. Now, what this means is if you go out and you're doing the Find Planets observation project and you mark down Uranus and Neptune, I know you're just using an app. You're not actually seeing it with your eyes. So how is it that we discovered these? So again, before the 1780s, Uranus was not known. To people before that time, the solar system ended with Saturn. It was actually discovered in 1781 by William Herschel. Now, William Herschel was not trying to find a planet. He was actually trying to find comets. He was doing a sky survey looking for comets. And he noticed this thing, and at first he actually thought it was a comet. However, he continued to track it, and after tracking it for a while, he realized that it was on a circular orbit. Then, discussing it with other astronomers, they came to the conclusion that it actually had to be a planet, another planet in our solar system. Well, as we have studied Uranus, we've actually found some very weird things. One, it is that it is tipped over on its side. Okay, so usually planets rotate with their equator close to the ecliptic. That is not the case with Uranus. Uranus is actually tipped over on its side. Okay, so it rotates like this as it goes around the sun, like this. It's really, really weird. Okay, what this means is during the summer solstice, the pole of the planet is almost pointed towards the sun. Now, one possibility for how it got this way is giant impact. If you remember previously, we mentioned that almost anything weird going on with the planets, we blame on a giant impact. Okay, so maybe Uranus formed correctly up and down as we would expect, but then it got hit really hard early on, which tipped the whole thing over, leading to it being on its side. Now, although that is a possible explanation, I actually just read something in the last couple of weeks from an article that suggested that maybe early on it actually developed a giant ring system similar to what we see around Saturn. And because of the gravitational interaction between the ring and the planet itself, it actually slowly twisted it over on its side, which is a very interesting possibility. So as astronomers started to study Uranus and its orbit, they noticed that its orbit was off from the prediction of Kepler's laws. It was off by about 2 arc minutes. Okay, well, this shift actually caused some people to start questioning Newton's laws of motion. If you remember, we derived Kepler's laws from Newton's laws. Well, that seems a little bit weird, so people started suggesting maybe Newton's laws work great on the Earth, but if you get too far out, then no, it doesn't work anymore. Well, there were two scientists, Urbain Jean-Joseph Leverrier and John Couch Adams, who both independently suggested that this shift in the orbit of Uranus might actually be caused by a planet even farther out whose gravity is pulling on Uranus. So both of them started to figure out and try and determine the position of where would this planet have to be to cause this shift of a couple of arc minutes in the orbit of Uranus. John Couch Adams actually finished his calculations first and sent his information to the London Observatory. After a couple of nights of observing, they didn't find anything. They wrote back and said, no, there's nothing there. Leverrier, although he finished his stuff later, sent his findings to the Berlin Observatory. And the Berlin Observatory was actually able to find the planet after just half an hour of looking. So they were able to find it really quickly. That's how good Leverrier's calculations were. After finding out that they had just been bested by a Frenchman, the London Observatory went back through to figure out how it is that they missed it, and they found that their star charts were actually outdated. They likely had actually seen it, but because they had bad star charts, they missed it. So, generally, the discovery of Neptune is actually shared between Leverrier and Adams, but really it was kind of Leverrier. Something that's interesting about all of this is that Neptune is actually the only planet to have been discovered because of our understanding of how it is that the laws work, that we actually discovered it through calculation based off of our understanding of physics. Or at least this is true, the only planet in our solar system that this is true for.